Here we're going to go over a problem that was in the lecture notes, but for some reason we didn't go over in class, so we're going to take this video to go over it. It's an example of the Henderson-Hasselbalch equation. We have a buffer solution which contains 0.1 molar acetic acid, sodium acetate. By this I mean that the total concentration of acetic acid and sodium acetate at pH 4.77 is 0.10 molar. We're asking the question, how many moles of H plus can be added to 1 milliliter of this buffer solution before the pH changes by 1 unit? The pKa of acetic acid is 4.77. Use the Henderson-Hasselbalch equation. All right, well, let's write down the Henderson-Hasselbalch equation. pH is the pKa plus the log to the base 10 of the base form over the acid form. B is base, A is acid. The equilibrium we're looking at is HA, in equilibrium with H plus and A minus. And we have pH, in this case, is equal to the pKa. That's interesting. So pH is equal to the pKa. What this implies is that the concentration of HA at this pH is equal to concentration of A minus, because when the pH equals to pKa, you're half titrated. Also, we know from the problem, HA plus A minus, total buffer concentration is 0.10 molar. So this means initially, before we add any acid or base, the concentration of HA is equal to 0.05 molar, and the concentration of A minus is equal to 0.05 molar. So the sum of them has to equal 0.1, and one has to equal the other. All right. So before we add any H plus, pH equal to pK, so we have 0 is equal to log of B over A, and B is equal to A, so this quantity is equal to 1, and log of 1 is 0. All right, now let us change things. Now let's add some H plus. Okay, and we want the pH to change by how many units? When we add H plus, it goes down, so we want the change in pH, delta pH, to be equal to minus 1. The pH goes down by 1. So initially it was 4.77. To change the pH, we want it down to 3.77. So the change in pH is 1. So this means that minus 1, change in pH, is a log of the base over acid. Now this is after addition of H plus. All right, or let's take 10 to the minus 1. That's 10 to the log of B over A, or just rewrite this, 0.10 is equal to B over A. Also we know from conservation that B plus A is equal to 0.10. All right, so here we have two equations and two unknowns. We want to solve for the acid concentration. The acid concentration will tell us after we add H, this will be the acid concentration. We'll compare that to the acid concentration before we added, and then see how much H plus we added. All right, let's solve this first equation for B. B is equal to 0.1 times A. Plug that in down here. So now we have 0.1 A plus A is equal to 0.10. Solve this for A. A is equal to 0.10 divided by 1.1. That's equal to 0.0909 molar. So after addition of A, we have this much H plus. Before addition of A, we had that, where was it? This much of the acid form. All right, so by adding acid, we went from this to this concentration. So the change in H plus was, we started, well, let's do it there, 0.909, that's after Initially you have 0.05, so the change in the H plus concentration is 0.0409. All right, so we made that much more acid. How many H plus did we add to do that? Well, 0.0409 mole per liter. And we have 1 milliliter, 1 times 10 to the minus 3 liter. Okay, let's go back to the problem. We start with 1 milliliter of the buffer system, and now we're adding some H plus to change it by 1 unit. This is the calculation of buffer capacity, and buffer capacity is an extensive variable which depends upon amount. So that's why we have to figure out that. So this comes out to be 4.1 times 10 to the minus 5th mole of H plus. So when we add this many mole of H plus to 1 milliliter of this particular buffer, we'll lower the pH by 1 unit.